That's the audio section. We've got the volume control pot hooked into the circuit. I've got a red and black wire coming over to apply power to the circuit. What I've done a little differently though is I have an 8 ohm resistor across the output so that I can get a fixed load when we get ready to do some frequency test later on. I'm just paralleling off it right now with a set of clip leads over to a speaker. So I've actually got a 4 ohm load on the output of the audio amp, but it will still work just fine that way. And we'll remove the speaker when we get ready to do a frequency response test. Okay, now for the moment of truth. We'll connect the plus lead up, see if we get any indication. Hopefully there will be no smoke. I'm hearing a pop. That's kind of a good indication. I don't see any smoke. That's another good indication. So let's take and just apply an input to the amp, and the easiest way to do that is just touch the capacitor. That's the input, and we should inject enough noise we should hear something. Well, I don't hear anything. So now we get to perform the first troubleshooting step. We're going to turn up the volume control pot. I thought it was all the way up. It's all the way clockwise. We're going to turn it all the way the other way and test it. And we can touch the input. So it appears the volume control pot's wired backwards. Well, so that was a good start on troubleshooting. Maybe not a good start on construction, but that's an easy enough thing to fix. All I have to do to fix that is reverse these 2 wires on the pot. I've got shielded wire going up to the board. This is a ground side. This would be the wiper here, the variable control. This would be the hot side. So if I reverse the ground and the hot side, that'll make the pot turn the other direction, and it'll be right to where when I turn it clockwise, I'll get an increase in volume. Counterclockwise will give me a decrease in volume. If it didn't work, there's a process we want to go through to make sure that things are what we think they are. Power is applied down here. I'm not using the diode. I'm hooked straight to here. We'll hook the diode in later on. So if I check at the junction of the 100 ohm and the 220, I should have somewhere around 12 volts. So that would be a good first spot to check. So always check your power first, and we'll check it there. And the other place we want to look for it is over on the IC. Now, one thing we need to remember on this particular schematic and all the ones I've seen on the web, pin 5 and pin 6 are reversed. Pin 6 is actually the power pin. Pin 5 should be the output pin. So we'll check it there to make sure we've got power on both sides of both on pin 6 of the IC, which is the power pin. And the other thing we want to check is the ground pin. To verify what I had to say about the pins being reversed, all we had to do is download the data sheet from the internet, and we'll see that pin 6 is VS source voltage, pin 5 over here is the output. What we will need to check also is we want to measure the voltage here on pin 4. It says ground, yes I know, and ground should be 0 volts, but if you had a poor solder connection here on pin 4, there will be a voltage there. So we want to check pin 6 to see that there's 12 volts there. We want to check pin 4 to see that there is 0 volts there. And if we have that, we should function okay in the circuit. First we'll check the junction of the power supply, the 220 and the 200 ohm resistors, and that is right at this point right there. And once I get a good connection, it says I have 11.7 volts there. My power supply is running a little bit low, but that's okay. It'll work there. I can turn it up, but I'm going to just leave it alone. That's close to 12 volts. We said we wanted to test the VS, the source voltage on the IC. That was pin 6. Now what you have to really be careful about here if you're using a probe this size is it's real easy to short things out. So to get to pin 6, I start here at the identifier, the little dot, right below its pin 1. So I go 1, 2, 3, 4, 5 on another side, then pin 6. So it's the second one over there. So I'll come and try to not short it out. It's kind of hard to do this while I'm filming it. Okay, I have 11.2 volts there. So we've got a little bit of voltage drop coming through the resistors. That's okay. Then the other thing we needed to check on the IC was the ground. Ground was on pin 4. So that once again we start at the dot for pin 1. 1, 2, 3, 4. So 4 is right next to the capacitor here. And I don't have any voltage there. So that's probably okay. So we should be okay with the IC circuit if you put all the parts in the right place now. Going back to the schematic, our power came through the 220 ohm resistors. To the IC it went through the 100 ohm resistor, went to pin 6, and like I said, pin 5 is incorrectly marked. Let me fix that. Okay, now that's better and I don't have to keep correcting myself each time I talk about the schematic. So power came down through the 100 ohm resistor over into pin 6 on the IC. Power also comes through a 220 ohm resistor, goes through a 4.7k ohm resistor, and ties to the collector of the transistor. The emitter of the transistor is at ground. So if we look on a transistor, the voltage between the base and the emitter, the base here and the emitter, should be 6 to 7/10 of a volt when the transistor is in operation. So if I have 0 volts here, I should be able to look at the base of the transistor here. So you see 6 to 7/10 of a volt. If the transistor is not operating, there'll be no current flow through the 200 ohm, through the 4.7 to the collector, so I should see the full 12 volts or so up here if the transistor is not operating. So we're going to check and look for voltage, the voltage on the collector first, then we'll look for the base voltage, and that should be about all the voltages that will tell the story of this circuit. I like to use the metal case transistors because in most of them have the collector tied to the metal can. So all I have to do is touch the metal can and it'll give me the collector voltage. It's a lot easier than trying to probe under the transistor. So this says I have 2.2 volts on the collector, which means the transistor is conducting. See if we can get down to the base of the transistor. That's a little harder to do. The base of the transistor is tied to a 120k resistor that has a 100 picofarad capacitor across it. And on the opposite end, the collector side has the 4.7k. So I can just look at the 120k resistor. If I read 2.2 volts, I'm on the collector side. And if I'm on the base side, I should only read 6 to 7/10 of a volt. 120K is the brown, red, yellow one there. So I'm going to touch the resistor lead there, hopefully without shorting everything out. And I have 2.2 volts there, so that tells me I'm on the collector side. So I need to go to the other end of it. On the other end, and I have 7/10 of a volt. I can change the range of the voltmeter. And it's about 0.64. Textbooks will tell you that base voltage on a typical transistor is 6/10 to 7/10 of a volt. Most of the time, unless you're running a whole lot of current through there, they're right around 0.65 or so. So that transistor is biased, it's conducting, and everything's working right DC-wise in this circuit. If you wanted to do some further calculations on this circuit, we know that we have a 120K resistor here. We have 2.2 volts here. We have 0.65 volts on the other side of it. So it's got a total drop of 1.55 volts. We could take and use Ohm's law, I is equal to E over R, and calculate the current. That current would give us the base emitter current of the transistor. We could multiply that by the gain of the transistor, and we would know the collector current. So if you want to try to do further calculations, I'll leave it to you to get a transistor book. My signal generator will only go down to about a millivolt output, so what I'm going to do is use a step attenuator, and we're going to start out with a 100 millivolt signal. See, it's five divisions in the scope screen. My attenuator is calibrated 10 dB steps, so we're looking at voltage. So every 20 dB, for every 20 dB I increase the attenuation, my output will go down to 1/10. Dealing with voltage, 6 dB will give you a doubling or a 1/2, and 20 dB will give you a 1/10 or a times 10. So I'm going to dial in 20 dB, and our input decreased. I'm going to increase the setting on the scope. I'm down to 5 millivolts, and we'll trigger that and adjust the vertical, and you'll see I now have 10 millivolts peak to peak. If I take and go down another 10 dB, I should be 1/10 of 10 or 1 millivolt. Another 20 dB, I should be 1/10 of a millivolt. We don't see that on the oscilloscope because the most sensitive position I have in this plug-in is 5 millivolts per division. I now have the top trace on the scope hooked up to the collector of the transistor. The bottom trace is the input to the transistor on the base. This is a common emitter amplifier, so I get the 180 degree phase inversion. This is a 0 volt reference line, and what's happening is our signal is going positive and negative around somewhere around a 2 volt reference, DC reference up here. Remember when we measured the collector voltage measured 2.2 volts. So what this signal is doing, the input signal is doing, is varying the DC voltage on the collector plus and minus around the 2.2 volts. When the input is negative, it turns the transistor off more, so the collector voltage increases. When the input signal is positive, it increases the forward bias on the transistor. The transistor is going to conduct harder, and when it does, we get a negative going voltage on the collector. So we should be able to increase our amplitude here, and if I increase the amplitude coming in, I'm going to do it on the generator here in just a second. If we increase the input amplitude, we should get an increase in output amplitude out of that transistor stage. I'm going to increase the amplitude of the input signal using the signal generator. And as you can see, the output gets bigger. Now we're about to encounter a problem down here. At this point, that's 0 volts on the collector. So if I go down to there, I can't make it negative. I have no negative voltages available. What I've done is increase the forward bias so much, the transistor will go into saturation to where an increase in input will not cause increase in output. Well, it will cause an increase in output, but not symmetrically, and we'll be getting distortion. So you can see it's flat topping. I'm still increasing the positive amplitude because I can turn the transistor off, and I should be able to increase that all the way up till I get to the 12 volts that I had applied, and you can see that's what it's doing. But we're causing severe distortion when we're doing this because the output waveform here doesn't look like the input waveform, so we have distortion. So we're going to knock that back down, and right about that point appears to be the maximum input I can put in. And if we look at the voltage, that appears to be about 20 millivolts, but 20 millivolts is an awful big signal in a receiver, so we probably wouldn't expect to see that much there. If we did see that, I think that some of the earlier stages would be overloaded also. Okay, but all we have to do left to do now is just to test it. Let's listen to the speaker. We'll take in, we have the dial set now to 20 dB. I was putting in 100 millivolts, so this is 10 millivolts going in now. I'm going to add another 20 dB into it, so I have 1 millivolt going into the amplifier. So I now have it set to 40 millivolts, and we're going to adjust the volume control up. And there's still plenty of drive and volume. This is only turned up just a little ways. Let's put another 20 dB in, so that would make a total of 60 dB. So I'd have about 100 millivolt on 100 microvolts going in. At this point it's quite a bit quieter, and I can turn the volume control up 100%. So what that tells me at this point is that as long as I have 100 microvolts coming into this amplifier from the BFO stage in front of it, I will have plenty of volume.